Last class was on forward Z transforms. So the idea is that you've got some sort of x of n, and you can find its Z transform, which is the sum of x of n, z to the minus n. So you'll notice it's very notationally compact. It's easy to compute. If we are working with signals that are, if I'm doing any kind of theoretical work with a signal, I'm going to use the Z transform because this is the simplest to manipulate. It also converges for the widest possible number of inputs. Remember, the DTFT doesn't exist for a lot of things. The sequence 2 to the n has no DTFT. Sequence of 2 to the n has a Z transform. It just simply doesn't exist for all values of Z. It only exists for absolute values of Z greater than 2. I don't care because I'm never going to keep that Z around. I'm just going to inverse Z transform it at the end, and the Z's go away, and I get my answer. Remember, this Z is complex, and if you were to graph the magnitude of this guy, remember, this is complex output, and it's a complex input Z. So it's complex input, complex output. Can't graph that, would require 4 dimensions to graph that. But if you were to graph the height of this, maybe we could graph just the magnitude of x of Z versus then this plane, this flat plane, would be the input. This would be the real part of Z, and this would be the imaginary part of Z. And so every value along this flat plane, then we plug that into this Z transform, and it would have the magnitude would have some sort of height. So that would be a surface in 3 dimensions. This is our unit circle over the Z plane. So this is magnitude of Z equals 1. And if we replace Z with e to the j omega, it's the same thing as this, where this angle here is omega, the angle it's making relative to the real axis. And so if we were to plot the height of x of Z around this line, we'd end up with a DTFT. So the x of e to the j omega magnitude is just the height of the Z transform plotted around this unit circle in the Z domain. So that's what we covered last time. Any questions about that before we go back into the inverse Z transform?
Yeah, can you explain why when you have a discrete, like a finite set, and you take the Z transform of it, it blows up at x equals 0?
Oh, sure. So here's an example of an x of n. And we'll make it a simple finite length sequence. And you can read out your x of Z directly from it. Now, in general, your x of Z is a ratio of polynomials in Z. But for this particular one, because this is the same thing as saying you can represent it as just a sum of impulses, sum of delayed impulses. This particular x of Z, it's still a ratio, but its denominator is 1. And so it just becomes 1 plus 2 Z to the minus 1 plus Z to the minus 2. So here's our 1, here's our 1, here's our 2, Z to the minus 1 plus 1 times Z to the minus 2. And Eric's question is, why should this thing ever blow up? Because it's a finite sum, so how could it blow up? And the answer comes if we write it. Remember, there's different ways to write this in different notations. One is in Z to the negative 1, but the other is in just plain old Z's. And writing in plain old Z's, you can see it's algebraically, this is the top is the same thing as the bottom, different notational style. And then what is this for Z equals 0? You can see this blows up. And it's the only finite Z for which this blows up. So we'd say that this is true for all magnitude of Z greater than 0. That's why it blows up at 0. Does that make sense, Eric? You divide 2 by 0 and you get infinity.
Gotcha.
Sometimes it just is that simple. All right, I am going to brief the rest of the talk off your student notes, which are a downloadable set from the website. What do you hope to accomplish with Z-transforms? The same thing we did with the Laplace transforms in EE431. We have an x of n, and we send it into our system. And out comes a y of n. Now, the reason why we're doing it in discrete time and not continuous time, because it probably really is a continuous time system since we're in the real world, but it's because we can compute this. We can sample our input, and now all of a sudden, once we've sampled our process, it's discrete. And so now we're shackled with the realities of having to live in a discrete world and having to deal with weird things like aliasing and a DTFT that's repetitive, whose highest frequency is only pi instead of in the continuous world where it's infinite. So that's unfortunate. But the fortunate thing is that by allowing ourselves to go in the discrete world, we can compute our output using a convolution. If you're in industry, that's what you're going to do. You can build a convolutional kernel that works real time. So as new values of x n come in, unlike MATLAB, which requires you to have your entire x of n first before you can convolve with your h of n, I will show you later on with a little bit of C code how you can convolve it in real time. So as individual things come into x of n, you can immediately compute it. It's convolutional output. It's great. This is not good, though, for anything to do with theoretical development, because you know convolution is that summation, which is painful to do. Instead, it's much easier if you're working with theory to take a Z-transform. So you take your Z-transform of your input, you take your Z-transform of your system, and now, instead of having to convolve the two, since you're in the frequency domain, you can multiply the two. And then you take the inverse Z-transform to get you back. So this is why, big picture, we're using Z-transforms. In industry, you're going to shoot right across from here and stay in the time domain. With theoretical development of filters and things like that, anything in grad school, you're going to go down this pathway and work it by hand. And last class, we talked about how to go from x of n to x of z. In this class, we're going to talk about how to do the inverse. So that's the big picture about why we're doing this. Any questions on that?
Sir, is that supposed to say h of s or h of z?
Oh, shoot. Thank you. I'm teaching EE430 at the same time, and it's easy to get mixed up. Yep, these are all h of z's. But if we were in the continuous time domain, this would be x of s, h of s, y of s, and everything would be the exact same thing. And you even remember probably from EE430 how to take that inverse Laplace. Remember we divided through to make it a proper fraction, and then we did partial fraction decomposition. We're going to do the exact same thing in the z domain. So let's start talking about it. I've summarized the book into 3 pages. I distilled about 20 pages of text down into 3. And I broke it apart to make what it's doing, I think, a little clearer. There are 4 ways to take inverse Z transforms. One way is analytic, and that means you end up with an equation, something like minus 0.06 raised to the nu of n. So an analytic solution lets you find the response for any time at all. For 1,000 is as easy as 1. And that's different than the numeric approach, which is you compute individually number out answers. You never get an equation. If you want to find the 1,000th response, you got to firstly crunch through 1,000 numbers. By hand, you take the analytic solution using the partial fraction decomposition, which works just like it did in continuous time with Laplace transforms. You make the fraction proper, and then you'll do a partial fraction decomposition. And then you match the parts with a table. In MATLAB, you can do it using residue Z, just like you used residue in continuous time. While this is nice from a theoretical standpoint, you often don't need to get an equation. You often just want to get numbers. And if you want to get numbers in MATLAB, you'll use the filter command. You've already been exposed to that in the lab. And soon I'll give you some C code to let you compute this even faster and in real time. Sometimes though, you only care what the first couple of values are. You want to see if the filter initially gives you some, you've built a system and you want to quickly see by hand, are the first few values of it before the filter settles down going to be something horrendous, like, you know, 1 million or something. And to do that, I'm going to show you how to do it using long division. This is going to seem like magic when I first show you how it works.